Hello, welcome to 13 Universal. This is A-level CIE Biology with Shedro. So we are doing now planning, analysis, and evaluation paper 5. That's series 5. We've done 1, 2, 3, 4. So watch those videos and then how we do it. Okay. Make sure that you have read these topics AS and A2 syllabus before you come over here. However, we are here to help you. You know, but what we do is that we apply concepts. So get your writing materials. Let's get into the show. Okay. Yeah. So remember, just like we always say, paper 5, has to do with they're creating scenarios and asking you to design experiment, evaluating and analyzing data. Okay. Remember that you have to read the background information very well and remember it. Okay, look at this. Antibiotic resistance um, resistance in bacteria is a global problem that has caused scientists to research into antibacterial substance other than antibiotics. Honey has properties that make it a good antibacterial substance. For example, honey contains hydrogen peroxide. So we pay attention to things they are mentioning. Hydrogen peroxide, which is known to kill bacteria. Wow, that's amazing. The most effective honey tested so far for antibacterial activity is Manuka or honey. Manuka, where can I buy Manuka honey? It contains less hydrogen peroxide than many other types of honey. So it contains less. So you pay attention to that. It contains less. But it does contain hydrogen peroxide, but it contains less. Okay? So every word is very important. Every sentence is critical. All right. But it does not contain an but it does contain an antibacterial compound, another one called methyl glycol, MgO, which is not found in other types of honey. So it has MgO. Other honeys don't have it. A student decided to investigate the effect of two antibacterial substances on bacterium Bacillus subtilis, which respire aerobically. Very important. Remember, it respires aerobically. MgO in Manuka honey, an antibiotic solution. These are things we're given. You have MgO in Manuka honey, then antibiotic solution used in cell cultures to prevent contamination. The student wanted to find the lowest concentration of each antibacterial substance that would kill or inhibit the growth of B subtilis. Let's go, guys. Question A. The student used a broad culture for the investigation. To make a broad culture, so follow them gradually, a small quantity of B subtilis, that's the microorganism, is added to a clear nutrient solution. A fresh newly made broad culture of B subtilis is also clear. Fig 1.1 is a diagram of a fresh broad culture of B subtilis. So guys, look at it. This is, yeah, fresh, right? It's clear solution. Fresh culture contains B subtilis, right? Please don't drink this, okay? Now look at this. AI says a sterile cotton wool, this cotton wool is sterile, was used in the top of flask containing the flesh broth culture of B subtilis to protect the culture from contamination. So they put it there to protect other microorganisms coming in. Okay, want to ensure that it's only B subtilis that's here. Now, this is your first question. Okay, solve this. So explain why it is better to use a sterile cotton wool bung, a sterile cotton wool. Okay, bung. Okay, this is it, cotton wool bung. Why is it better to use this? All right, containing in a flask containing broth culture of B substance rather than using a sterile rubber bung. So cotton wool bung and rubber bung. Why is it better to use cotton wool? So pause the video and try to um answer the question. So write it on your book right now, the reason. Okay, write it. Okay, pause the video and do that. Now, why? Because they told us that, guys, watch. They told us from beginning that B subtilis is anaerobic. Sorry, is aerobic, is aerobic organism. If you go back, you see that Aerobic means it requires oxygen to carry out respiration. So why we use cotton wool bung instead of rubber is to allow oxygen into this, all right, medium. Why? Because the B subtilis, all right, respires aerobically. Okay, oxygen is needed. Okay, let's see what the masculine says. To allow oxygen to enter for respiration, because all right, this respect. So they told you this. The problem with this, if you forget what they said at the beginning, you must remember what they said. That's why we encourage you to practice a massive reading. Okay, just one mark. Let's go. Before comparing the two antibacterial substances, the students carried out a trial experiment. It's a trial. Let's go. The student transferred a sample of fresh blood culture to a culture tube and incubated. To be sure, substance is there, B substance is there. The tube at 25 degrees Celsius for 24 hours. Fig 1.2 summarizes the result of the trial experiment. That's it here. So this is, all right, the tube, okay, and once it was incubated at this temperature, can you see? Turbid. It becomes turbid, cloudy. That means the bacteria, they grew, they increased in number. All right, that is why the turbidity increased. Okay, this shows bacterial growth. No growth here, there's growth here. This shows the bacteria has grown. How do you know the bacteria has grown? Turbidity. So they are giving you clues that this is how you know the bacteria has grown. The solution becomes turbid or cloudy. That's turbid or cloudy, right? Shows bacterial growth. Okay, let's go. The student decided that turbidity of the broad culture is a measure. See, every information matters. Is a measure of bacteria population growth. Is a measure of bacteria population. That's turbidity. Is a measure of bacteria population growth. That's bacterial growth. Explain, give reason how this concept can be used in an investigation to measure the extent of bacterial growth. How do you measure the extent? Pause the video, try this question, okay? Do it yourself, all right? That's what we recommend. Then you check and hear the solution. All right, so now how do we check, measure the extent? How do you know how the extent bacteria has grown? So the extent bacteria, remember that bacterial growth, okay, is a result of turbidity. All right, so how do you check the extent? So that means that the more bacteria, right, population, the more bacterial growth, the more turbid the solution becomes. And how you measure that? Because how do you measure that? You can measure turbidity either by using, by viewing it using okay, white card at the background, viewing the solution to check how cloudy it is, right? That's a subjective way of measuring it. Or you can use colorimeter, right, to measure the absorbance. Okay, that also, right, is another way to measure it. Okay, look at it here. Population growth, bacterial growth increases. Okay, it becomes cloudier or more turbid. Yeah, the more it grows, the more cloudier. How do you measure turbidity? By either eyes against a cross background, okay, well, with a colorimeter, or either use colorimeter or turbidity. This is subjective, in your eyes. All right, now using turbidity meter or color chart. Okay, so let's measure it. Okay, let's run. Now we have a lot to do, guys. Question B. The student decided to test the antibiotic solution before testing the Manuka or honey. All right, antibiotic and Manuka honey. They want to test. Two of them have antibacterial activity. All right, in addition to normal laboratory apparatus and materials, the student was provided with, number one, a fresh blood culture of B subtilis. Number two, a clear antibiotic stock solution. The stock solution. Now, of course, the next one, nutrient solution to dilute. Now, nutrient solution to dilute. See, to dilute, not distilled water. Nutrient solution to dilute. You see, pay attention. The antibiotic stock solution. 15 cm cube flat bottom glass culture tubes with sterile cotton wool bungs. A choice of graduated pipettes to measure volumes accurately: 0.2 cm cube, 2.0 cm cube, 10.0 cm cube, and 25 cm cube. Okay, pay attention to background information, guys. Let's go. The student prepared dilutions of the antibiotic stock solutions and added a volume of each to different culture tubes. All right, added a volume of fresh. So the next thing he did, he added a volume of fresh broad culture of B substance to each tube. After adding, all right, the prepared solution of the antibiotic solution, I added this, all right, because allow time for bacterial growth to occur, and then check each culture tube, recorded and analyzed the results. Okay, decided on the lowest concentration of antibiotic solution that appeared to kill or inhibit the growth of B subtilis. They said the first question, they said outline a control for this part of the investigation. So try the question. So what is a control? Outline a control. I'll try. What will be the control? What is causing, all right, the growth? What is affecting the growth? So a control means remove what is affecting the growth. Okay, which is, because what we're working on here is, this is antibiotic, okay, stock solution. So you can remove the antibiotic solution and replace by distilled water. Okay, it is antibiotic solution that is antibiotic that is determining the growth or turbidity. So replace what is causing change with another thing, distilled water. Is that okay? All right. Replace antibiotic with distilled water, or if you don't want to use distilled water, replace it with nutrient solution. Just one mark. Let's go. In the next part of the investigation, the student used a stock of Manuka. Now, it's done with antibiotics. Now it's time to check Manuka. Please remember, immersive reading is very important here. And you are working against time. So you have to read line by line, think sharp, within a short space of time. But it's okay. Practice will make you better. Now, the students remember that hydrogen peroxide, yeah, they said it at the beginning, could be present but could not think of a way to break down the hydrogen peroxide, because we want to check now both hydrogen peroxide and Manuka have antibacterial activity. If you do not remove the hydrogen peroxide, you would not know, okay, whether it is Manuka or hydrogen peroxide that is actually affecting the growth of bacterial population. So the student has to remove this. If they say he does not know, okay, he could not think of a way to break down the hydrogen peroxide to remove it from the solution. You are the boss here. You are the supervisor. Just checking out what a student has done. That's what Paper 5 does for you. You stand as the examiner, you're looking and you're evaluating. This is teaching you about how to, demonstrate higher order thinking skills like evaluation, okay, analysis, synthesis, and all of that. Now, the question says, describe how students can improve the investigation by removing hydrogen peroxide from the Manuka honey solution, and explain why this improvement makes the result more valid. Okay, remember, you pause the video, that's the drill, and you attend the question. Pause it right now. I'm watching you. Okay, do it. It's good for you. Pause the video and work on it. Okay, welcome back, guys. Now they say describe and then explain. There are two command words here: describe and then explain. So describe how the student, now if you start thinking about what can break down hydrogen peroxide, what do you know that can break hydrogen peroxide? Okay, catalyst, yeah, catalyst enzyme. So treat the Manuka solution with catalyst enzyme, all right, or peroxidase. Is that okay? Or any other chemical. And then, of course, why are you doing that? Because you want to ensure that bacterial growth is only affected by Manuka, not hydrogen peroxide. Okay, now look at it. Can improve, add catalyst, peroxide. Okay, you know that. Explain why. Results, okay, or killing of B subtilis bacteria is only due to honey or Manuka. All right, not due to, okay, it's not due to hydrogen peroxide. So 2 marks. Now the student was provided with a stock solution of Manuka, this is Manuka nut, honey containing an mgl concentration of 600 milligrams per cm cube. This was a clear solution labeled 100, so labeled 100% honey. The same apparatus and materials were used. Now here we go again. Describe how the student could prepare 100% solution of honey using the stock solution. Construct a table. These are two questions. One, describe how this will be prepared from stock. The second one, construct a table to show the dilution show the dilution is made for 100% solution and the other concentrations that student could use. Yep. So pause the video, attempt the questions. Okay, you can do it. Pause it. All right, welcome back. Remember that the first one says, how do we produce? Okay, this is a beaker containing 100%. So you should show how we can use 100% stock to produce 10% concentration. See, so this beaker containing 10%. So remember, guys, it's simple how you're going to do that. Okay, now they didn't give us the final volume, okay, because you're going to take from here, take a particular volume from add here, but see, we are diluting. Well, what were we provided to dilute? The nutrients. Okay, you're not diluting water, so you add a volume of nutrient solution. Okay, so you take a particular volume. So they said describe how students could prepare 100% solution of honey using stock. Just say that a particular volume of the stock is taken, added to a beaker, and it was diluted using a specific volume of nutrient medium. Okay, not distilled water, because they provided nutrient medium from the beginning for dilution. Is that okay? Okay, so because they didn't tell us the exact volume to prepare, so we couldn't mention the V1 and final volume. Okay, but see this, they say construct a table to show the dilution is made, from for the 100% solution and the other concentration, sorry, 10% solution and the other concentrations that student could use. So this is simple dilution. So they say we should prepare a table to show other concentration that could be made. Remember that if you're going to vary your independent variable, this is 100%. So we're going to choose concentration between 100 and 0. Okay, because we can choose 10. You know, maybe if you're coming down, for diluting down, start with 90. Does that work? Well, if you start with 90, that will be too much. You need 5. Okay, we need 5. So if you do 90, okay, 90, 70, okay, 50, 30. Okay, and yeah, that's what that works. Yes. So we are going to have 90. Okay, all right, remember that you must have an interval that is the same. So the next is, okay, 70, right? Next is what? 50. So between 90 and is just, okay, yeah, the next is 30. Okay, 30, yeah, and then the next, the 30%, okay, is of course 10. We've been shown how to do it. So these are range of concentration. We're adding 3 more to it apart from 10. Okay, so 10%, 90%, 70%, 50%, 30%, 10%. All right, so let's assume that they say we should construct a table to show the dilution is made, how the dilution is made for 10% and other concentration. Okay, now because we can't work on this without, we need to get final volume. Let's assume that each concentration we should produce final volume of 20. Okay, that's 20 cm cube of the final volume of each of these concentrations. That is the final volume. Okay, now you have it. So the work is easier. So let's draw the table. Pardon my drawing tool. So look at it. All right, so I want to produce, this is a table. Okay, yeah, so this is the heading of the table. That's a heading. Okay, so let's go, guys. Remember that this is the concentration, right, of Manuka honey. Okay, so I call it concentration of concentration. So conc, I'll just say conc of, yeah, Manuka. Manuka is MgO, right? So MgO is a cute name. MgO, yeah, MgO. Okay, that's good. So remember, you put the percentage. The unit is percentage, right? Concentration is in percentage, right? So you put it right. Put in bracket, or just use a line to show, right? Okay. So in percentage. Now, of course, the next, okay, we use volume of stock. The volume of stock we're using, volume of stock, because you must, that's our V1. So you're taking from stock, which is 100% to produce other ones. So volume of stock, just make it brief there. Volume of stock, okay. So make sure you're following. Volume of stock. Stock solution is 100%. Okay. So this is simple dilution table. Okay, volume of stock, and you know what unit is volume measured in? What is the unit of volume in this context? Yeah, of course, is cm cube. Cm cube. Put it in bracket. Cm cube. Okay, and this is volume of nutrient solution, the one you're using to dilute. So volume of nutrient solution. Okay, yeah, nutrient solution. Nutrient. So just call it NUT, nutrient solution. Okay, yeah, nutrient solution as the volume of nutrient solution, and of course it's in cm cube, guys. All right. Remember, the volume of stock plus volume of nutrient solution will give us final volume. All right, good. So I'm gonna draw 5 of these. This is 1. Let's go. Let me clean it. Yeah, sorry. Yeah, let's go. Okay, make sure you're drawing. You must have drawn your own by now. Okay, yeah. So now that is one of your questions there. We are trying to respond to this question. Okay, good. Remember that the first one here, concentration we have to prepare, is 90. Okay, 90. We have 70. Now you can choose to start from 80, but make sure that the interval runs the same down. Okay, 80, 60. So I'm doing 90, 70, all right, 50, right? So you can do 80, 60, 40, 20. Okay, all right. Now this is going to be 30. Okay, okay. So just 5, but this thing must be the same. The interval must be the same, right? So now remember that all we need to get is V1 for each. V1 is volume of stock for each, and you know, from dilution formula, V1 is final concentration, which is each of them times final volume. That's V2, C2, V2, okay, all over C1. C1 is the concentration of stock, which is constant, right? So if I want to calculate for 90, the V1 for 90% will be 90 is my final concentration. Is that okay? So 90 times my final volume is 20. I got that, right? They didn't give it to me, but I needed something, right? Yeah, you can choose 10 too, right? That's the volume. Now, 100 is our C1. That's the stock. Every other one is going to be made from 100. So that would be 18. Okay, V1 is 18 for 90. So that means I'm taking 18%, 18, sorry, cm cube of the stock. How much of volume should I, volume of nutrient? Okay, this nutrient solution, how much of it will I add to make it 20? That will be 2, right? Yeah. So So I go again for V2 for 70, V2 for 70, sorry, V1 for 70, yes, the volume of stock for 70, V1, let me correct it, please, that's V1, okay, for 70, quickly. So we have, of course, 70 is going to be my C2 there, okay, times 20, which is my V2, all over C1, which is 100, yeah. So what is the answer there? That's 14, okay. So this is that 14? Yeah, that's 14, right? 14, is that okay? Yeah, 70, okay, 7 times 2 is 14. 9 times 2 is 18, okay. So you're going to add, how much of water will you add here? You add, okay, 6, right? Is that okay? You add 6 to make it 20, okay. So you see that we're removing 4. So we have found the pattern. Keep removing 4. 14 minus 4 is what? 10, right? Yeah. So this is going to be 10. Add 4 to this. See, I don't have to calculate it all the time. Once I find the pattern, this is going to be minus 4, 7, right? Is that 7? There's going to be 6, right? 10 minus 4 is 6. 10 plus 4 is what? Okay? So you're going to add, of course, how much of this 6 plus what will give you 20? 14. So 10 plus 4 is 14. All right. So this is going to be 2, right? And this is going to be 18. So guys, we're prepared the table. Okay, that's it. Okay, you have questions you can ask. All right, let's go to see what they said about the answer. All right, so they said description table for 10, or description or table, we've mentioned that take a particular volume, right? Correct method to dilute stock, Horn solution to, okay? So we're using, of course, the stock here is 100, okay? So we use series simple dilution, at least 5 dilutions including the use. So all of these are there, and their units, nutrient solution including their unit. Okay. Now state the independent variable and dependent variable for the part of the investigation involving Manuka-Horn solution. So what are we changing? Remember, independent is what you're changing. Dependent is what you are measuring. So what are you changing? So state it. Write it out now. Okay, we're just changing or varying the concentration of Manuka. You just saw us do it. Okay, we just did it now. Vary, produce 70, 80, 90, or 90, 70, 50, 30, 10, and all of that. Now what are we measuring? Bacterial growth, which is measured of turbidity. So independent variable is concentration, honey. Dependent is turbidity. 2 marks. Very cheap. Predict the result the student would expect when investigating the effect of Manuka honey on bee subtilis. Explain the reason behind it. Okay, they say predict that they're asking us indirectly, but try it first. Predict the result. Okay. So what do you think is the result? What trend? They're asking you the trend. What is the trend between your independent variable? Your independent variable is concentration. What is going to be the relationship between independent variable here, okay, which is concentration of Manuka, and turbidity? Okay, try to predict it. Turbidity or bacterial growth. Is that okay? Turbidity represents bacterial growth. Okay, I will leave that top. Concentration. So is it going to be a negative one or positive one? Okay, what that means is that as concentration increases, okay, what happens to turbidity or bacterial growth? As concentration of Manuka oil increases, what happens to this? Turbidity will decrease as concentration increases, right? As concentration decreases, turbidity will increase. Why? Because as concentration of Manuka honey increases, more bacteria will be killed. Remember, this is antibacterial to kill bacteria. So they have, if you like, you call it, okay, negative correlation or inverse. Okay. All right. So as concentration increases, that turbidity will decrease. Okay. That's what I said here. Predict Lower concentration tubes will be turbid, yes, or cloudy. So the ones that have lower concentrations, they'll be very turbid. Or you can say high concentration tubes will be clear, not cloudy. Yeah. So you see that? Yeah. Or the lower the concentration, the more turbid. Yes, that's cloudy tubes. Okay, they just added the tubes because we have to tailor it to see the context. Explain Manuka oil inhibits growth or kills bit subtleties. Okay, lower concentration have less ability, so MGO to inhibit the growth of. So that's why it grows more at lower concentration. All right, 2 marks. All right, describe how students could determine the lowest concentration of Manuka honey solution that would kill or inhibit um, the growth of B subtleties. Do not repeat detail, okay, that's antibiotics, details on how antibiotics, different concentration was prepared of Manuka honey solution. Do not repeat it, and do not give details of using aseptic technique to prevent contamination of students, the environment, or other people. Okay, so describe method. Method always comes out, guys, right? So remember, the way we do it is that you have to you are writing an essay here. So to write an essay, you need an outline. How are you going to? Don't just jump into this. Get an outline. So identify your independent variable, IV. Your independent variable is concentration. So how do you change it? How do you vary it? That's what we do. Well, they say we should not mention how we vary it. So go on and dive into what they want. Okay, now how we varied it was just dilution. Dilution was how you, that's how you change concentration, you dilute. Now dependent variable dv is turbidity. How do we measure it? So you measure a dependent variable, so you must, so how do you measure it? How are we going to measure it? And you're going to place this in a logical order, just like as if you are in the lab doing this. So dependent variable, you are concerned with how to measure it. Independent, how do we vary it? Okay, and then your key variables, how do we standardize it? Key variables, how do we keep them constant? So this should be on your outline, guys. I've always said it. Have an outline before you go into this essay. It's a descriptive essay, all right, a prose. So these are the things running at the back of your mind, is your plan. Okay, before you start writing, you must have a plan before execution. Planning is very important. Now, okay, you're going to talk about, okay, how do I produce reliability? All right, reliability, okay, that's RE. You know, you're going to have to do repetition, reliability, repetition, okay, RT, and all of that. Reliability, and of course, yeah, hazard. What's the hazard? The precaution, the risk. So, how many items are here? About 5 items, right? You must think about them before you start writing, and take them one after the other. Okay, this is what runs at the back of your mind. So you start off here. Now this said, they say you should not talk about this, but you're sure you're going to talk about that, of course. How you measure this, all right? Of course, what are the constant variable here? The volumes of different concentrations of Manuka should be the same. The volume should be the same. Okay, the volumes and the concentration of nutrient medium should be the same. All right, of course, yeah, that of the bacteria, we should have the same concentration or volume of bacteria, B subtilis, the same temperature for all of them. These are things that affect, these are key variables. Temperature will affect them, of course, pH will affect them. All right, keep it constant. But how do I start? Of course, you just say that you take, of course, you're not using personal pronoun. Okay, all right, just say that particular volume, same volume of Manuka honey, and the nutrient medium are put into a beaker and mix. They're stirred, and then you incubate them, right, in the same temperature, okay, for 24 hours, and then after that you now measure the turbidity using colorimeter, okay, and then you have to repeat it for each concentration. Do at least 3 replicates and calculate the mean. And the hazard here, you mentioned things like B subtilis is a hazard. Is this a a pathogen can infect you, so you wear gloves, mask. Okay. Now, of course, we are dealing with all those antibacterial, antiseptic, and all of that. They are also hazards. Then honey can also be an allergen, so wear your mask. All right. So this is simply okay. Yeah, what you should do. You see, same stated volume of culture brought, same stated volume of manuka honey. Stir them. Okay. And of course, method of turbidity, that's colorimeter. Put in colorimeter and measure. Idea, write down, record which concentration. Yes, we didn't mention this. So because you need to find out the concentration, the lowest concentration that gives us the clearance. So you check. Once you measure, you can measure that absorbance, or you measure by viewing the turbidity. The one that gives you the clearest solution, the lowest concentration that gives you the clearest solution, is what we're looking for. This is how they determine the dosage of antibiotic. Call it sensitivity test. Okay, the lowest that gives us the result. All right. Then of course, method of maintaining temperature: put in water bath, thermostatically control water bath. Time left in, mention the time, pH buffer used to maintain pH 3 times. Okay, find mean. Now see the hazard. So run away from the hazard. Live cultures, okay, allergy, infection. This is what to do. Wear gloves. Honey can be allergic, so wear gloves. Broth, irritant, wear gloves. Okay. All right, guys. 5 marks, not joke. Look at this. Quickly, let's read fast. MCI, methicillin resistant Staphylococcus aureus, is an example of antibiotic resistance in bacteria. There's evidence that medical grade Manuka honey is effective in treating wounds infected by MCRA. This honey has been sterilized by gamma radiation and filtered to remove contaminants. A study was carried out to see if another type of honey, Germania honey, is as effective as Manuka honey in killing bacteria. Okay, remove from wound of 50 people with, this is MRSA, not N. 5 different concentrations of each type of honey were compared. The concentrations were numbered 1 to 5, with 1 being the highest concentration and 5 concentrations and 5 the lowest concentration. At the concentration of course 1 being the highest, okay, and of course concentration, and 5 the lowest concentration. That's what I'm trying to say. At the concentrations where there was no visible growth in a broad culture of S. aureus, the researchers transferred samples onto nutrient agar plates containing no antibacterial substance. Incubation of these plates confirmed that there was no bacterial growth. The results were analyzed using the chi-square test. That's chi-square test. All right, good. See chi-square test. All right, see the chi-square test here. So you see, this is concentration. This is the first one. Second, this is first. Comparing them, this is Manuka. Number of growth. So number of growth is, check the trend first. Number of growth. This is number of cultures with no bacterial growth. Can you see that Manuka, number of cultures with bacterial growth? So Manuka is less or true. That means it produced, is more effective. Okay. G1 than Germania. Okay. We can see that here the chi-square value here, all right, is 5005. So significant, yes, significant. Okay. Now of course the difference here is also significant. Okay. So this is, what should this be? Should it be yes or no? You can see it's also significant. Look at the difference between them. All right. Yes. Check this one. The difference between 11 and 30, 39 and 20. See it? Chi-square value here should be yes too. But if you check these, the difference is not much. So no, not significant. Okay. So M5, and look at this. You can see the difference is not much. That's why not significant. Okay. But if you check, you see that for the first one, from number 1 to number, because if you are asked to evaluate this, for example, all right, whether there's actually a difference between them. Okay. Yeah, what are the difference between the activity of Manuka and Germania is different. If you are to evaluate this result, what are you going to say? If they ask you to evaluate you're going to give reasons based on this data why the difference, there's a significant difference between this and this, Manuka and Germania. Okay, you can also give another argument, right, that there's no difference. For example, if you check this, the difference is significant between the first one, second one, third, but the fourth and fifth, the difference is not significant, right? But the concentration, this 1 2 3, okay, you can check significant, yes, yes, you can see. So you can see that generally that Manuka has higher effect on bacterial growth. So even the number of culture with no bacteria, see that they, okay, all right. So you can see number of cultures with bacterial growth. Okay, so this killed many of them for each of them. So Manuka has higher, more effect from 1 to 3. Okay, now even across the board, is that okay? Yeah. So why is it not? Of course, yeah, if you consider this is significant, right? Now this is a statistical test, right? And check here, the first one, the chi-square value is 5.005. This is 13.306. This is 14 point, all right, 932. So the significant ones are from 5 and above. Okay, this is below 5, not significant. Okay, let's look at what it said. They said table 1.1 shows the result of the study and statistical analysis using chi-square test. Yeah, look at chi-square. These are chi-square calculated values, right? They are calculated values. They were compared to, right, the tabulated value. All right, there's a state a null hypothesis for this investigation. So try it. 1 mark. What is null hypothesis? That the difference in there is no difference, all right, because it's negative, not negative. There's no difference in the effect or effectiveness or effect of both Manuka and Germania on the growth of B subtilis. Okay, the difference between their effect activity, there's no difference, right, on their effect. They have the same effect. That is null hypothesis for you. Okay, so look at it here. That's what it said. There's no difference in the effectiveness of Manuka and Germania. So null hypothesis always is a negative hypothesis. It says no difference, no difference, no. Enter say null. Remember to say no difference, no. Say no. All right. Okay, let's go on. Now table 1.2 shows some critical values of chi-square at different probability. You can see that. Okay, this is the tabulated form of this. Okay, tabulated form. You can see now if you compare to the other one, can you see that the degree of freedom, because we had only 2 samples, Manuka and Germania, so degree of freedom for chi-squared is always, that's V. All right, V is always determined by saying n number of population minus 1. Okay, good. So n here is 2, okay, minus 1. So V here is actually 1. Okay, so if you come here, guys, and follow this one, if you see, look at this from here, you can see that the first one was 5.0005. You see that it is greater. And remember, we said for you to make decision about significance or not, remember that we always say that always compare chi-squared calculated, that if chi-square calculated value, the first one we did, is greater than chi-squared tabulated value, if it's greater than chi-squared tabulated value, okay, so reject the null hypothesis. That means the difference between the effectiveness between of Manuka and Germania, okay, is significant. The difference is significant in that, all right? If this is greater than this, if chi-square calculated, all right, and if you check from the other table, the chi-square calculated is actually greater for number 1 under this critical probability 0.05. Okay, number 1 was 5.0. 5.0 is greater than this, okay, but it's only for this. Number 2 is about 13.0 something, which is greater than this. And this probability is greater. So there's no significant difference here. If you check 0.01 probability, it applies across board for 2, 3 also applies across board. If we check 4 and 5, all right, they are less than, the calculated value is less than this and this. So there's no significant difference for 4 and 5. Okay, all right, so just try to make sure I explain more. You use table 1.2 to decide whether the chi-squared values for concentration 2, 3, and 4 in table 1.2 are significant or not significant. Write your decision in the final column or table. All right, write yes if the value is significant, right? No. So we have said that the first one, of course, they said here. The second one, if you check the chi-squared, right, calculated with this, you see that is 13.0, 13 point something, and that is greater than this, so it's significant. If you check the second one, 14 point, which is greater than this, remember that if this is greater than this, the one on the table there is calculated. If it's greater than this, then there's significant difference, right? So if you check 4 and 5, they're all less than, right? They're less than, yeah, they're less than this, yeah. Okay, remember this is where we are. Okay, less than 3 point something, so they are not significant. 4 and 5. So the second one will be yes, right? The second one will be yes. The third one not significant. All right. So go check it. Go check it, guys. Just one mark. This study compared the effectiveness of 2 honey varieties in treating wounds infected with MRSA. State the conclusions that can be made from result and statistical analysis of the study. All right. So what conclusion can we make? We have stated there, right? You can see that if you go back to that table, you see that from number 1 to 3, all right, the difference is significant because the chi-square calculated values are all greater than the tabulated value, so it's significant. And if you check a general trend there, that the Manuka honey has more effectiveness in inhibiting the growth of B subtilis than Germania. That's a general trend. But you see, 5 to 4 or 4 to 5 is not significant, all right, according to the statistical table. All right, look at it. Kills more bacteria, more effective. Statistical analysis, 1, 2, 3 are significant different. Okay, last two are not because they are less than the tabulated value. Okay, one is significant only at 0.05. Is that okay? 2 significant at not just 0.05 but 0.01, 0.01. Okay, yeah, so 2 marks. Yeah, let's go to the next one. Let's run, guys. So hosting cattle have been selectively bred for their high milk production. We're dealing with evaluation more now. The seed of the cotton plant Gossipum species is a good source of fiber, protein, and carbohydrate. Just pay attention to this to improve milk production. Whole cottonseed meal can be added to livestock feed. Cottonseed meal is cottonseed. So cottonseed meal is what? Cottonseed that has been processed by grinding. That's the meal. Fig 2.1a shows whole cottonseed, and Fig 2.1b shows cottonseed meal. So this is cottonseed. A shows cottonseed, right? So this shows cottonseed meal. So watch them. Whole grain processed. Okay. Free gossipol is a toxin found in cotton seeds. Yeah, it's a toxin there. So follow them. Follow. Let's go. Some of these free gossipol binds to protein to form bound gossipol. This occurs during microorganism fermentation. Free gossipol is easily absorbed. So this is easily absorbed, so less toxic. Okay. Bound. Okay. There's a bound gossipol is easily absorbed, so it's going to be more toxic. Okay. Yeah. But bound gossipol is absorbed less easily, and it's not toxic. Okay. So let's go. An investigation was carried out on the effect of different dry matter diets on lactating milk hosting cows. 30 healthy cows were fed on the same cottonseed free for 14 days. Why would they fed cottonseed free? So think about it. Why they started with that. The cows were then divided equally into 5 groups, A to E, and fed on one of 5 experimental diets for 42 days. One on the quantity of milk produced each day was recorded. So they were changing their diet, and they're measuring the quantity of milk. So which one is independent variable? Which one are they changing? Diet. Which one are they measuring? Quantity of milk. Do you see it? The cows had no visible signs of illness during the 42 days. For each diet, table 2.1 shows the cottonseed content and total gossipol, free and bound. Okay, the meal daily dry matter taken in during feeding intake. The mean daily lactation performance, that's milk yield, is also measured. So this is, guys. So once they give you a table, check the trend. There's different groups. This is different description of the dry matter diet that we are given. So you see cotton seed, right? So right, so look at it. All right, okay, so you can see, remember, we're checking the different quality. So now, but which of them, okay, gives us the highest? Okay, what's the general trend? Okay, the one that gives us highest, which one is okay? 32, that's E, mixed 2, okay, followed by what? After that, followed by, so it's going to be E, followed by B, so whole seed. Wow. Okay, all right, so followed by what again? D, and then C and A. So A doesn't have any whole seed, doesn't have gossipol in it. These guys has gossipol, and they even did better than the guy that didn't have gossipol, right? But guys, if you check, this see this test, this standard error, this is plus or minus. Okay, now if you add plus or minus for this, this is plus or minus 4, plus or minus 3. If you check each of them, you see that there will be overlap. Overlap means it will show there will be no significant difference between them, right? But isn't that all of them are high and they are similar to each other? All right, and if you do overlap here, for example, if I add 4.7, 77.6 plus 2.3 and I minus it, I do the same for this, I do the same, so that there are going to be a lot of overlap. Do you want us to try it? Okay, let's try it. Let me do this and this first. If I say 28, all right, 28 point, this is 28.7, okay, in terms of milk yield plus 1.3. all right, it gives me 30. So for this, look at the overlap here, guys. When I teach you, you show others. Now this is 30, that's the highest, all right? Highest, what should be the lowest? Minus it. Just the same 28, 28 point, okay, 28.7, okay, minus 1.3. What does it give you? It gives 27.4. Yeah, okay, now that's for that one, 27.4. So we are trying to look at trends. Okay, now this is for this. Do the same for this one. For E, I'll just say 32.6 plus 1.3 for milk yield. Okay, that's 33.9. That's the highest is 33.9. 33.9. okay, yeah. So let's check the lowest. So 32.6 minus 1.3, what should it be? All right, the lowest is 31 point, okay, all right, 31.3, okay. So it seems there is no overlap. There's no overlap between D and E, okay. But if you try for C, 27.9 plus 1.3, I'm just teaching you how to do it. 1.3, okay. So what is going to be 29 point? So this is good. So the highest is 29, right? 29 point. This is 29 point 0.2, right? So that's 0.2, right? 29.2. Okay, now if you want to find the lowest, so you say 27.9 minus 1.3. We're just trying to look for overlap. All right, now that's 26. That will give you 26.6. Now 26.6. Can you see there's already overlap between C and E? So 26.6. What do I mean by overlap? 29.2 is inside this range. Okay, it can be found here. Do you get? 28 is inside here. 27 is inside here. It's only 26 are out of it. There's overlap between this and this. You can try for the other ones. All right, you can try for the other ones. So they say the difference in the dry matter intake for group A to E were not statistically significant. Yes, they were not statistically significant. A to E. Where's A to E? Yeah, they mentioned why. Because where you can find overlaps. There was no overlap between this and this, but if you check, you're going to find overlaps. Okay, are you following? You're going to find overlaps. Let's go. So now the answer: explain why the cows were all fed on the same cottonseed free diet for days. Remember that we're testing to check the effect of the gossipol, which is found on cottonseed. Try to solve this question. All right. So we fed them to ensure that none of the cows had gossipol. Okay, to make sure that the diet they took were free from gossipol, to make sure that gossipol was not present from beginning. So all right, so standardize that. Okay, see, to ensure that no gospel cow, to remove gospel from cows. So no gospel idea feeding on the same diet, standardized cow, starting experiment. So now using the information provided and the results shown in table 2.1, a student made some statement about the effect of feeding different diets on lactating host. Okay, student stated that if the investigation is repeated, the groups of cows will produce milk in this order. So the highest, of course, that's what we have there. So if you repeat it again, we're going to have the same thing, right? E is highest, B, D, C, A lowest. Okay, A is lowest. So with reference to table 2.1, explain why the statement made by a student is not supported by data. We have already mentioned why is not supported by this data. Okay, that they will produce this. Okay, why is it not supported by the data? With reference to this, that E, B, D, C, A. So we should give evidence that does not support that this statement. What statement? Students stated that if the investigation is repeated, the groups of cows will produce milk in this order. The highest is going to be this. Of course, lowest is going to be this. Okay. So now there are a lot of evidence. For example, you already know. Look at it. See the table. Of course, now this is showing us that we have a lot of overlap. So significant difference. All right. Not significant difference between A and B. There's overlap between A and C, A and D, B and C. Okay, there's overlap there. And of course, if you check also, you find out that, guys, that the results are similar. The results, is quite similar for A, B, D, C. Okay, from what we showed the other time, A, B, D, C, they have similar results. Okay, and if you check, you find out that A cannot be compared because A does not even have gossipol. It doesn't have cottonseed, so it shouldn't be part of the consideration. But A, B, C, D, they have similar results. Okay, they didn't give us any information on the percentage of gossipol and how it affects milk production. Okay, milk yield. So look at it here. So the mean yields are very close, are similar. All right, there's no statistical test. We didn't do chi-square t-test, so that's against it. Always check out for statistical test. There's no statistical test there. All right, there's overlap. We did see overlap here. Okay, this does not support it. okay, in the sense that they are similar, they overlap, right? Details of which groups are not. So this overlap, all right? So there's not significant difference. This may be significant different, A and E. Okay. So scientists are developing cotton plants that are genetically modified to produce seeds lacking gossipals. Seeds lacking gossipals. Table 2.1 suggests that there may be a link between total gossipal in the diet and milk yield. So they are connecting gossipal and milk yield. Okay, they're saying there's a correlation. The student stated that repeating the investigation with no gossipal in diet B to E would result in a lower milk yield for each group. This is what the student is saying. This student, why is he stating this? Or is she stating this? That repeating the investigation with no gossipal would result in lower milk. Now, before you go into this, so this student is implying that no gossipal, that gossipal has effect on milk yield. Okay, that's what it's implying. So, guys, it's saying that there's a positive correlation between gospel and milk yield. So if you have no gospel, milk yield will be less. Then the question is, explain whether or not table 2.1 provides enough evidence to support the statement made by the students. Students is saying there's a relationship between them and a positive correlation for that matter. So look at this. Can you see that? Yeah, all right. It supports it because look at gospel, total gospel, the ones that have high, all right, amount of total gospel gives high milk yield, like E, okay, followed by B, right? And of course, if you check also, you find that as total gospel, that's going to say it increases, the milk yield increases. The ones that have low gospel in the diet has low. Look at this, has low, the lowest, yeah. Okay, follow this has lowest and it has lowest milk yield. Okay. Now, if you check it again, you see that this doesn't support because A doesn't have gospel and it still has high yield. Do you get? It still has high yield. All right. Okay. Okay, we can see there. All right. So you can see A group A has no gospel and it still has high. There was no information on the amount of gospel and how gospel affects milk yield. All right. That affects the result also. Look at it here. The trend as gospel increases, milk increases. You quote data, not evidence. There's no, because anytime you're evaluating, remember that you must state the evidence that supports this hypothesis and evidence that does not support the hypothesis. That's evaluation. Okay, remember we're dealing with high order thinking skills. So now these are the evidence that support the hypothesis, that but these are the ones, right, that either no information that differentiates that differences in milk yield is caused by differences in gospel. You can see no information on nutritional content. There's no cotton seed. Okay, so A cannot be compared. Can't use A. So there's no statistical test on this. Always mention there's no statistical test is always a big plus. Okay, look at the last um I think the next question is, higher concentrations of gospel absorbed into circulation can cause an illness in cows known as gospel toxicity. Low concentrations of gospel can be detoxified in liver. During investigation, the gospel intake for each cow was measured and analyzed. At the end of the investigation, 40 days, day 42, the blood plasma gospel concentration of each cow also measured. Fig 2.2 shows the free gospel intake for each cow plotted against concentration of gospel in plasma on day 42. Look at it, guys. You can see free gospel intake. All right, this is plasma. You see the plottings. Okay, so the question says, with reference to fig 2.2, which is this, explain whether there's a relationship between free gospel intake and plasma gospel concentration on day 42. Okay, guys, you can see that there is a correlation, a positive correlation, right? As free gospel intake increases, the plasma gospel concentration also increases. So there's a positive correlation there. All right, there's a relationship there. All right, shows a positive correlation. That's correlation there. Okay, now gospel produced by cotton plants can be found in two forms: the negative isomer and positive isomer. The negative isomer has the higher biological activity within cells and is much more toxic than the positive isomer. Both forms can bind protein to become bound gospel. Table 2.2 summarizes the mean daily gospel intake for the 5 different experimental groups of lactating hostile cow. So please make sure you remember what I'm saying here, okay? The one that causes toxicity is the negative one. The one that doesn't cause toxicity is the positive isomer. So if you look at the table, we work with table. You can see. So which one gives us the highest, all right, isomer? This is this, okay, because it has the highest, all right, gospel intake. The one that has the lowest, because there's no gospel intake in group A, so 0. So there's no toxicity here. The one that has highest toxicity is E, followed by the next one, B. All right. So the experimental data, guys, will always show you a trend, and I'm telling you, make sure you spot out the trend. There's always a trend in the pattern, and that's a skill you must learn. Okay, that's data analytics. Look at it. The investigators knew that the different diets presented different levels of risk of causing gospel toxicity in cows. For example, the diet for group A cow did not present any risk of toxicity. Look at it, because it has no intake of gospel, and therefore the negative one, which causes the toxicity, is not present. You can see that. Okay, let's see what they're asking us to do. With reference to table 2.2, discuss the extent to which the different experimental data for group B, C, D, E present a risk of causing gospel toxicity. So anytime they say discuss, they wanted to give a structured reason from the experimental data that supports, all right, the argument. You must write for and against, all right, the argument, all right. So let's look at it first. If you check that data, you see that the highest is B. Okay, let's look at it. The highest is E. Yeah, check it, because E has the highest gospel intake, so it will cause more toxicity. The lowest is C. C has the lowest gospel intake. All right, it will cause less toxicity. Do you get? And then of course you can see that as toxicity is affected by the amount of gospel intake. All right, so but there's no statistical test. You cannot bank on this. All right, but look at it here. So the highest is this. Okay, the more toxicity, the more gospel intake, the more toxicity. The lowest is that. Okay, so there's no statistical test. All right, and of course if you check, you can also find that. Look at it here. Has highest, this has the lowest. Okay, reference to free gospel, highest risk. So the one that has the free gospel has highest risk, like I've mentioned. Always quote data. Free gospel will easily be absorbed, so the ones that they are not attached to the protein, so they easily absorb, they get into the blood, and once they absorb, they cause more toxicity from the beginning of this question. All right, guys, thank you for following up. Leave your comments, okay, and if you have questions, make sure you share this video, okay, and like it. See you next series. Bye.